Good.
Well, you use that in like finance a lot. Mrs. Gordon, you often do something funky with my keys.
I what?
I got it now, but often when you like throw these back through, there's a key sticking through the gate, and it's like really awkward. I'm like, does she need a puzzle for me?
I'm purposefully. I have.
All right, so homework tonight's 105 to 107. Only 3 problems, right? But please check 107 in the back with your checkpoint. It's a checkpoint problem. There's answers and everything
I
else.
don't have 3 problems.
Yeah, but they're multifaceted problems. So there's like multiple parts to it. So one thing that I found really funny while watching The Office the other day. Well, not really funny, but circumstantially funny.
Good afternoon, Piper Beth. Please come to the office. Piper Beth, please
I
come to
wait
the
for
office.
Gunnar and
Thank
he
you.
leaves. Where do you go?
There you are.
I wait for you, and then you leave.
No, I went to go start my pencil.
Who said that, dude?
Okay, so I was watching The Office the other day, watching back through the season's while I'm just getting work done, just having it on. And there's a scene in there where Andy is interviewing for a regional manager, and they're asking him all these ridiculously difficult questions, and he's obviously getting them wrong. And then they ask him, what's the distance between the Earth and the Sun? And he goes, oh, I know that one. It's 93 million miles. And that's approximately like exactly what it is. 93 million. Like for us, turning some insignificant values into zeros, we can approximate it to 93 million miles. So that is the radius of the circle. Since we don't, quite exactly make a circle, that's the radius, of our path. Yeah.
How do people figure that out?
Calculations. I mean, you can just observable distances and refraction of light, and really, we could actually figure it out through the reverse method. If we know we travel a year's worth of time through one rotation around the sun, right? Because when we rotate once, that's a day, and when we rotate the sun, that's a year. Yes, right? Or do I need to go back to science?
No, that's right.
Yeah. Okay.
Yeah.
So, what we are now going to calculate was information like what they used to figure all this out, except we know the radius now. So, if we say that our path is if we say that our path is a circle, even though we know it's elliptical, with a radius of 93 million miles, how far is that in one orbit? Now, if you'd like, work in millions of miles.
I feel like 93 degree diameter.
Now that would, we couldn't just do 93 if we were dealing with area, right? But here we're dealing with linear distances, so we could just look at 93 and then tack a million label on whatever we get.
And then we're finished with 100 feet. Hours. We got about
You guys are already kind of on beat.
I got about 6,659.4.
Leave it in
I got
exact
67 here.
While working with it, if you can carry it in your calculator, you might as well.
Yeah, that's what I'm actually.
How do I figure out circumference? Pi times 2r, or pi times diameter. Here we have the radius, so we might as well use the formula involving that. So pi times radius times 2. I kind of like to write it like this sometimes, because then it's the same as area, except instead of power, it's multiplier. So I was talking about that with a student that I tutored last night. So we double our 93,000, or 93 million. I'm just going to work with 93.
I thought the radius was
What's
40.
Yeah, but the distance between sun and us, which means that's our radius, right? So 93 million is our radius. We have to double that. So double 93 is 186, right? That times pi gets us a circumference of what?
186
186 million. Oh, okay. So you're not giving it to me an exact. So I'll go ahead and write that 186. Yeah, times pi a million. I don't like that. So if we do decimal though, I think it's gonna be over 500, right? So guys, 584 million miles. Now, did anyone watch Cloverfield Paradox?
No.
Okay. Probably. Did I ask that question already?
Yes.
They end up on the other side of the sun. So, according to that, so there's this whole series, like, there's multiple Cloverfield movies, and it's all like, holy cow, what if, like, this could happen? What if multiple realities could kind of collide together? And they accidentally transport themselves from this side of the sun to the opposite side of the sun.
Isn't that just the future?
Well, okay, that's too far of a conversation for today, because that all depends on what you think about string theory and physics. But that is your 186 million miles, right? That distance across. So if they went exactly from where we are to the exact opposite side, that'd be 186 million miles away. So in the movie, they don't travel it. They ended up in a different reality. It's complicated.
Are they still on Earth?
Oh, well, they were never on Earth. They were in their spaceship. Like in a space station, really. It's. I'm not saying go watch it, because I forget what it's rated, and there's probably some bad words, but it's an interesting take on what ifs. Yeah, I'm not your parents. So I don't determine what you
My
want.
parents didn't let me watch Disney movies until I was 7. The only Disney movies I saw were 101 Dalmatians, Cinderella, and Beauty.
Are we ready to talk about B? Or you guys still saying?
Yeah.
Okay, how do we solve B? Do I have any volunteers to talk me through the process? You've been like running class. Jenny? Okay, well, good.
So you have to find distance, because we have to find the rates of miles per hour, so we have to use distance equals rate times time.
Not, I mean, you can. So, you're saying the same thing.
Yeah,
It's the same equation.
but we're just reversed.
So rate is distance divided by time. You are correct, but that is derived from distance is rate times time. You're both right. So,
the distance is 584 miles. Okay, over time, so which we calculated if it's hours, and this is 1 year, so that's 365 times 24, which is 87,860.
what? Okay.
8,760.
Oh my goodness.
Woo! Did you hear that attitude?
And then you divide it, and I got a really.
That happened.
Wait, what's that?
66,670.
Whoa.
Oh, that's
What the heck,
a
Jenny?
good number.
Jenny,
Jenny, what the heck?
Is that what you get?
I got 66,000.
Give me place that.
5.0.
That's what I got.
Yeah, see?
Is it 666,000?
It's about like 66 now.
66,000?
67 if rounded. How did you get that?
Wait,
Wait, okay, that's
66,000.
65.
No, I don't believe you guys.
It's
You're arguing.
66,705.
What if
Point five.
you guys-
Because you have to do. I put too many zeros. No, look.
No,
Look at this.
This is what I got.
So, wait. I have a way that we can figure out. Hold on, I have a way that we can figure out if we're right or not. Neil deGrasse Tyson just told us a piece of information we can use.
Oh, it's 800 miles an hour.
What was the question that had been asked?
Oh, what would happen if it stopped working?
For 1 second.
Mhm.
So
about
we
right. You
calculate
divide that by 8, it's a little.
speed per second. It should be 800, right? Close.
About
How do we get to speed per second?
you divide it.
something that I'm still not sure if my high school science teacher was lying to me or not. She called it stoichiometry, and I'm not sure if that's an actual word or not. Because Mrs. Bickle was an interesting teacher, but I love her to death. She was awesome.
I got 8 to know.
Yes.
Pickle. Like pickle, but pickle. Stoichiometry, at least the one that she used, is just unit conversion, right? We have hours, and we need seconds. Yeah, but I don't even know how she would have spelled it. She just always said it. It might be a real thing, but you know, she was kind of kooky. So we set up unit converter here, right? We can go straight to seconds if I know how many seconds are in an hour, or I can work my way there if I do minutes per hour and then seconds per minute.
3,600 seconds in an hour.
Or just as easily, I'm just showing you guys the technique. We can do this, because I want miles, sorry I should have had this, MI, miles per second, so I want seconds on bottom. There's 60 minutes in an hour, 60 seconds in 1 minute. So we just multiply across the numerator, divide it by everything in the denominator multiplied. Is it approximately 800?
I got
18.529.
I got 18 too.
18 is basically
800.
Yeah.
Yeah, it's real,
What?
you know, by approximate math. Do we think that's right? Do we think maybe we misunderstood? I will tell you, this is correct.
Yay!
Got it.
Wait,
So,
but that is miles
So we probably
So
miles per hour.
we also did a lot of rounding.
Yeah, but it
wouldn't be that off.
780.
These are huge numbers.
Now, still, let's think about this though. 18 miles in 1/1000. Like in that span of time. So, we'll go back to Neil deGrasse Tyson and see if we can make sense of why we got a different result than maybe what he said or why he said what he said. But this is absolutely correct. 66,705 miles per hour. That is the rotational speed of Earth.
was heavier and then would like. I don't know. Science is
You know,
a weird thing.
I've heard that women are self-conscious about their weight, and Mother Earth.
Oh!
Wait, was he talking about the...
Well, men can be self-conscious of their weight too.
We're not talking about...
Oh, like
That's
one
why
around the sun.
Thomas has
So-
strength training
so,
class just for
Now
females.
you gave it away. Can I move on? And we'll come back to that.
Thomas has a class just for females.
Ethan figured it out.
Yeah,
but
Wait, Ethan. In my second semester though.
we're going to come back to Ethan.
Doing
So, in designing items for consumer use, I have to wonder how they really think about maximizing profits, right? Because you walk this fine line of I want to minimize what we spend on an item, but I want to maximize the effectiveness of it because somebody's going to use it and they want to think it's good, but then it's going to probably need to wear out at some point, so they buy another one.
Oh, it's just like us buying a new car.
Yeah, so you want your car to work well while you use it, but then at some point you want somebody to buy another one again. So it makes me think about windshield wipers because I need a new set of windshield wipers, and you know, this is accurately placed during winter of our textbook. So after winter, most people have to buy new windshield wipers because they've gotten chewed up by the ice and everything else. So we're going to calculate, what do we call an area, a part of a circle? Sector, right? The arc is the length on the edge. The sector is the region. Now, do we have an entire sector here?
No. Wait. They should make a car that is perfect.
I love how I ignore that your hand's up, but then at some point you're just like, screw it, I'm just going to say it.
Oh, now here's this photo. So thank you. Ignores your hand.
Well, okay.
You're good.
But I mean, anyway, they should make a car that works perfectly, but it should have a thing that kicks in when it's like a certain amount of years old. where it just like everything
You know, like
stops
the iPhone.
working. Yeah.
Okay.
It just stops.
So, how, I'm not going to do this for you, but who can describe the method you're going to use to do this? How we can calculate just the shaded region.
Like calculate all the entire circle, and then take a third of that, and then subtract do it the same with the white circle. And then
Can I explain it better?
Yeah, sure.
Oh my gosh.
Line.
But I'm sorry.
Oh, I just have a question. Is the 15 the shaded area or the whole thing?
The 15 inches is here.
Oh,
The 5 inches is here. So the
That's
whole
not
wipe,
what
it's
I
a
was
20-inch
like.
wiper. So it's a 20-inch wiper,
Oh,
which
that's
is like
why
a
my
size of wiper.
calculations are
Yeah.
off.
Yeah. So the question answer stuff. Well, maybe how to do it. So what you could do is you have to calculate the area, like if that was a full circle. So it's just
Yeah,
it's like a real sector. You're just calculating a sector.
Yeah, so you're saying we get the sector from the whole circle. Like, how much of the circle would this be?
Yes, and then you figure out. You calculate the same thing, but just for the unshaded section. So it's just a little like 5-inch circle.
I found it.
That looks good.
Do we leave it in terms of pi or?
Yeah, sure.
What? Why would you make us do that?
You don't.
Or make it decimal. I don't care. I just said, yeah, sure. I didn't see.
Oh, we're finding that
You
just
didn't
white
say so.
area.
Just
Oh.
shade.
Never ever say that ever again.
Sounds like aided. Unshaded. Oh, I see how it's.
Did you say O and lightning?
Yeah.
Yeah.
What do we think? Can I get a verification, maybe? Isn't it 120 degrees is a third of my circle, right? So a third. Now that's just simplified from 120 over 360.
So it's 400 pi minus 20 over 3 minus 25 pi over.
I got 400 over.
Yeah.
Yeah, that's exactly what I have right now. Well, you didn't.
I think you guys argue over that.
No, did you subtract?
Wait, 4 times 4 is 60.
That's 400 pi minus 25.
I'm confused by your asking.
Oh, I learned one.
You have to divide
So what do we get?
first and then.
Yeah,
125 pi because this becomes 375 over 3 pi, which simplifies to 125 pi, which as a decimal would be, oh, might as well look at that.
392.699.
47. Oh, I did 100.
I don't like 9, that's just kind of, let's just go 7. Inches squared. Label your answer.
Oh yeah.
Any questions about
We did this on today for him.
so
that's brutal.
I don't think you're really asking the right question. I don't think they really have much of a feeling for you because they don't really know
we
you
don't have
that
second
well.
like combined lunches anymore. And we cheered like we were all like.
I
"Yay!"
understand why
And
you
then
guys
Miss
want
Smith was like, wait, hold up, tell me why. And we were all just talking about how we love this.
Well, I think
It was-
more of your
It was
peers.
really
brutal.
I think
It was so sad.
more of your peers were saying we want to eat with our 8th grade friends and we
Yeah,
don't really
but then
care
we
about
also
7th
talked
grade.
Yeah, that's it. That's pretty much what it was.
But also some
Hey,
mom said
just,
how they don't
hey,
like them.
I'm lobbing you a softball. It's an analogy. Quit being mean and just say, yeah, we want to eat with our 8th grade friends.
That's it.
Who said that?
Mine though, he said that all computers were
Only
Yeah.
most of that.
He did. We're not talking
No.
No, right after he gave the disclaimer and said, okay, sorry, only most of them were. So it's okay.
This pedigree was so sad.
Well, okay. So the reason that we had done that initially was because you guys, students, had asked to combine 7th and 8th grade more previous year. Like, so who knows? Next year they might want 7th and 8th grade combined stuff. I don't know.
I ever taught 6th, 8th graders last year. They all creeped me out.
These are fun problems. Maximization problems.
They are so wasteful of their.
Oh, I know. No. Every single bit of the problem.
Oh yeah, that is.
Oh, that's so
Oh, wow.
No, but you can just.
But then
So we know the real goal here, right? How much dough is wasted on a sheet, or like per cookie, really we can say, when the cookie is 3 inches.
It's a square.
So, let's, to make life easy, because we were working with something like this yesterday, let's assume we're going to have a 12 inch by 12 inch sheet. Right? We're going to cut out cookies. I would urge you to make your cookies whole inches. And let's say for whatever reason, because if you're actually making cookies, you could offset your cuts. Well, let's say you can't. Right? We have to have rows, columns. If you were actually making cookies, you'd probably offset your next cut and squeeze it in there. But we can't do that.
Yeah, why can't you just like take like the
Yes,
leftovers?
but then it takes time, right? And a bakery's like, quit wasting time. Just move on.
Why can't they
Make a giant
well, like along someone line, and it's
Why
just,
can't
like,
you guys just solve the math problems?
Because
You're
I am. I'm
a
almost
third
done.
degree.
They should just learn how to problem solve instead of me having to solve their problem.
Do we
with
need
math.
to terms of
square
Yeah, but this is
line?
how you make money,
I asked you an
solving
actual
other
math
people's
question.
problems.
If we leave it in terms of pi or not, because I don't think
Let's leave it in terms of pi because we need to compare here.
144 minus
Right.
36 pi.
In terms of pi, well, okay, so you're, sure, go decimal then. Your argument's good. That she's saying the whole sheet, if we set it to 12 inch by 12 inch, I'm just trying to make your life easier, because honestly, we could have skipped one of these problems, but these are fun problems to work through.
Wait, I have a problem here.
What?
Yeah.
So, if you find the area of 12 1-inch cookies, it would be 144 12-inch cookies. 1-inch cookies. Right, but it says that area, logically that area is bigger than 144, and that makes sense.
You sure you calculated correctly?
No.
So we have 12 inches by 12 inches. You're saying make 1-inch cookies.
Get this.
So your radius is not 1 inch.
Yeah, that's what I got.
Now, but what if I can make this easy, really, really easy. If I'm making 3-inch cookies,
Wait,
Hold on.
you make 2-inch.
What?
Whoa.
if every cookie's being cut from this hypothetical square sheet of dough, and they're all perfect circles, then really I can just look at one cookie. I believe we had problems like this in Math 1 if I'm not being crazy with remember. It's 4 cookies wide, it'll be 4 cookies tall, so we're going to have 16 cookies in total. If I just calculate for one of them, I can multiply by 16 to find all my waste. Right?
But how is that
Different
any
techniques.
easier?
It's, well, maybe easier wasn't very good. An alternative method.
Okay.
Just making sure you guys look at every option possible. So 3-inch cookies, my radius then is 1.5. Did anyone find the waste of a 3-inch cookie? Column?
3.9026455
Column?
I got 3.9026644
Per cookie? Oh,
Per cookie. Wait. Total.
I did I got like 30
3?
total.
Like 3 square inches? Like 3. Is that
16, 3
3-inch in diameter cookies.
Yeah, the
Had-
waist.
Is about 31 square inches.
Yeah, that's also 30.932.
So waist,
Wait.
31. 31 point what? Just give me tenths.
Well, it's 30.9. It's 92.
Okay, so approximately 31 inches square inches. Let's, do you want to make the cookie smaller or bigger?
I realized something.
I'm making an alarming discovery.
Same here. I think
I'm going to make my cookie 4 inches because that's easy to work with. 2-inch radius. 2-inch radius, right? So. So
We're not gonna share it before you discover it for yourself.
each cookie would be 16, or each piece would be 16 square inches, right? Minus 4 pi, right? Radius squared. So somebody calculate that for me if you would. Then we'd only be able to make 9 cookies, right? Less cookies fit, the bigger you get. So once you find each cookie, multiply that by 9. So multiply that by 9.
30.902664.
Oh, got it.
Yeah, good job, Jenny.
If I make my cookie, no, I remember where this problem's from. This is from 7th grade. I'm not good. There's a t-shirt design problem that does exactly this.
Are we like not allowed to call them
I
studies?
don't care. Yeah, I think a lot of those things are terms of endearment.
I don't know if that's
So-
7th grade.
I'm gonna come to you. 6 by 6
That's
36.
that's
minus 9 pi, right? And then how many cookies could I bake?
525,000.
What?
I can bake 4 of them, right? So if I multiply that waste, we get Colin. You said you made an alarming discovery.
Whoa.
Okay, so Ava and I both made this discovery. So I tested this with, of course, the 3-inch diameter cookies, 2-inch diameter cookies, and 1-inch diameter cookies. I found that for all of them, out of a 12-inch by 12-inch square of dough, they have the exact same area in total of cookies when you.
Which means the waist is the same. And I also
Yes.
tested it for bigger circles,
Yes.
so it's the same everywhere.
Why? Is there more area of dough? What's really happening here? As I kept changing my image, right, changing my numbers on there, my measurements, what was I essentially doing to the size of the cookie? Dilating. All we were doing, assuming that we were making it fit perfectly too, is creating a dilation as long as they're all perfectly taking up the squares. So as long as we don't have any partial cookies, because then the waste would get a little funky, right? There's more waste out here than there is in here. So let's say you end up at the end of your sheet with this much of a cookie, that will totally throw off your measurements, because that's not, say that's a fourth of your cookie, that's not a fourth of your waste, it's actually more. So as long as you accurately fill the space, it's always going to stay exactly the same. Cool. But your task was a goose chase, right? There's no way to reduce waste, because if we fill up the space completely, this is still going to happen. So your alternative suggestion could be what? I already kind of tossed this one to you also.
Use all of it and make a cookie cake.
Cookie cake,
Yeah.
square cookies. What if he still wants round cookies?
Wait, they could probably find. They could probably find the best compromise between most cookies produced and the type of cookies that the customers want the most, and then produce that, since the waste is going to be the same no matter what.
Change the size of the dough.
Ryan, you got another one? All of these have been good.
I was gonna say pour all the batter in there and make it like a whole giant square and then cut it
So
up.
that
Cookie
won't
batter.
work, by the way. You are showing that you have not baked very much, which is okay. You've got plenty of life to bake. We could also suggest they make some small cookies that we could get the dough out of that open space.
Yeah.
That's
Bow it all up.
Yeah.
Roll it out again. And then
Or
roll it
Gunner,
again.
who's obviously been in a kitchen, you just put it back together.
Yeah, we've done.
Yeah,
chef
so
will say
get your fat straight
that
before you
excess
bully.
dough, compiles it, and
Hey,
compiles
don't
it
use that
and
word
turns it into
like-
another sheet.
All right. Great ideas all around. We should make some cookies.
Yes.
So, there's like a dozen down.
But none of them.
What?
Radians. They don't know. Radians we've talked about for, a hot minute here and there. But remember that the radian measure of an angle is the ratio. If we're going to define what a radian measure is, it's actually the ratio of arc length to the radius for the corresponding sector. So, how far we've gone from how far from the center we are. Right? So, pinky travel compared to distance between pinky thumb. So what is the radian measure of a 45-degree central angle for a circle with radius 5 centimeters? Now, if you remember what I've referenced to you dealing with the unit circle, this should start to become pretty easy. If you don't, I'll remind you in a couple minutes. So dive in, give this a shot.
Oh my gosh. Gutter.
Yes.
Very nice. It isn't? Wait, like the arc length or?
Oh,
Wait, so the arc length is 2.5.
not verifying or denying.
Okay.
It's right. That means it's right.
Okay.
This is completely confusing. I don't understand feet.
I don't know. Wait, so
Wait, we're doing the first part of the problem, so like the 5 centimeters, right?
And then once you get beyond that, then try with, and lets you figure out what we're gonna realize here.
Oh, so try it with a different size?
like 10.
Yeah, so then it goes on to say, what about with 1
Oh.
centimeter?
Whoops.
I have my shoe around this stuff in my head.
What?
1 to 4. So it's 5 4.
5 4.
For the. Okay, I said.
Right? I mean, it's a catchy song. How much of the circle is 45 degrees?
1/8.
An eighth, right? So that arc length will be an eighth of our circumference. And our circumference here is 10 pies. So we have 10 eighths pi for the arc length. Yeah, if we leave it like that. Yeah? No? Yeah? We need to put that in ratio with. Now, if I look at 10 eighths as 5 fourths pi, divide by, or in ratio with,
And then you can cancel out and then you get 1/4 pi.
I can flip and multiply, or keep, change, flip, whatever method you want to talk about. We really.
Okay, we're good.
Pi to 4. Yeah? Try it with a radius of 1. Radius of 1.
What's the angle measure?
Wait.
Same,
yeah,
same
yeah.
central angle.
Wait, what's that number by pi?
10 eighths pi. This is
The
just a slash.
The other one.
This?
No.
1 eighth. 10?
Yeah.
10.
That's 10?
Sorry, yes.
40
No, sorry.
I mean, the circle. Hold on. Go back to
No,
your.
but look, Jenny, it's the same thing.
Wait,
We've already talked about this a little bit.
Don't listen to me.
He never listens in general.
Not true. I listen
That
to
is
a lot of
definitely
people.
true.
Not you. I listen to my sister. She's better.
Oh, wow.
1/4.
So 1/4 pi
Oh, no, that's the
compared to
same
1
thing. That's the same thing.
is still,
1/4
It's always
it's always the same because
similar. It's dilated in the circle.
Because all circles
it's
are
just a
proportional.
dilation. Everything's proportional. This is how we get our unit circle values, which is how, when you're on the $1 Million Game Show or whatever in the future, and somebody asks you what is the radian measure of a 45-degree angle, it doesn't matter how big the legs are. Your radian measure has no units, no labels. It's just the ratio. So here, pi over 4. If I go up to 90 degrees, pi over 2, right? We started talking about these. If I go to 180, pi. If I go to 270, 3/2 pi, I mean another half of a pi. And if I go all the way around, say somebody asked you for a radian measure of 360 degrees. Because the circumference, wait, let it sink in. The circumference
Pi r over r.
is 2 times pi times the radius. And the radian measure is just the ratio of circumference to radius. Right? Arc distance traveled. Alright,
Perfect.
that's really. Oh, so when it's pi over 3, that kind of gives it away for us. So if we know that pi relates to 180, then what's a third of that?
Oh, 1/3 of 180 is 60 degrees.
E would be 60 degrees. If we now know that pi is the radian measure for 180, then we can work from that. By the way, so Ethan, hit us with your knowledge of why Neil deGrasse Tyson's answer was different than what we were discussing.
Yes. So he was talking about the rotation speed of the Earth, not like how fast it goes around the sun. He's saying how fast it rotates around its axis.
How fast the Earth is spinning, not rotating. So it's like its personal rotation, not its orbit. So if we stopped orbiting for a second, we would lose 18-ish feet in our orbit. But if we stop rotating for a second, because we're small, we move fast, right? Smaller you are on, like, tighter in together you get, you're moving super fast.
Oh, I hate that.
800 miles in a second. So go watch that clip with Neil deGrasse Tyson if you want. Cool stuff. He was in Chicago when we were there this past year on the day that we were walking past the theater, and it broke my heart. But it was sold out, so even if I wanted to go. Mr. Estes and I looked at each other and we were like, should we go see Neil deGrasse Tyson?
Yes, you should.
Yes, but we had a whole group of 7th graders, so.
You should have